Okay, let's start show at the screen. Let me explain what's going on here. So this is your final book, and in order to give you an idea of how the things are split up here, in terms of how much you should give effort into. Okay, you should give, I would say, 80% effort in this book. Okay, deformation of solids right? Let's say just forget about it. And particle physics যদি না করায়, I don't think you will have a change in grade in your exam. You understand what I'm trying to say? So dharo, we didn't do deformation, we didn't do particle physics, you gave your exam, and you did these and gave your exam, right? I don't think it'll change your grade. Of course, mark it but it's not such a big topic that it can cause a change in your grade, okay? So these are very nominal questions. What I mean by that is particle physics question right now without doing the chapter, right? You should be able to answer 8 of them out of 10 because it is less than O-level particle physics. O-level particle physics ছিল হচ্ছে radioactivity, remember half-life calculation and whatnot. এটা ওইটাও না, এটা হচ্ছে কম। এটাতে we just learned about alpha, beta, gamma and their properties. There was a table we did in O-levels if you remember. Just that, okay? Deformation of solids হচ্ছে 50% already জানো তোমরা। 50% is the spring chapter. So F equals to kx, spring constant, Hooke's law, that. And then there's this addition here, which is like a improvement on that idea. Okay, it's called the Young modulus stress and strain. So that's like very small. What a formula to parle okay. But when it comes to these two or these chapters that you see here, especially wave properties and superposition, right? These are very complicated. I mean, if you ask any student who has given AS, right? There are students who just skip this. If they feel like it's a waste of time. Don't do that. Okay, I've seen like at the point the students start to compromise. Will I be able to finish my syllabus, right? Or a ways start because cover because it's complicated. Okay, so if you stick with me, it'll be easier because I'll tell you why they find it complicated. This is broken down into 11 different segments, and each of them are like a separate small topic. Okay, not a very big topic. A small topic and a new idea. Ideas. Okay, so that's why it feels very overwhelming, right? Everything is like new, and it's not the ways that you heard of. So, transverse wave, longitudinal wave, so that's like 1% of this wave chapter. So, rest is like what waves do with each other, how do they interact, what are the properties of waves, what are the behaviors of waves. Like you remember light chapter, diffraction, reflection. So this wave is entirely different from your O-levels. Our electricity, electricity, there are 2 parts to it. One part is the O-level part, like same to same, like your current key, voltage key, those, right? And then there's this other part, which is the circuit questions, right? Which are all very similar, but we have something called, some of you did electricity, the Kirchhoff's law. Kirchhoff's law, electricity, mastermind. Kirchhoff's law. No? Yeah, okay, fine. So KCL, KVL, দুইটা law থাকে, current হচ্ছে sum করলে কি হয়, right? That's only new here. তাছাড়া কিন্তু it's just O-level. So আগে থেকে বলে রাখলাম কেন? আমি তোমাদেরকে একটা timeline দিতে চাই of when I finish, okay? So my aim is generally to wrap up waves by December, like I must, okay? And electricity circuits এটা হচ্ছে January, and particle physics, which takes 3 classes, so it'll January. So usually this is the target. Sometimes it's earlier, sometimes it's a little later, but this is a picture for you, when we finish. So by January, must we spend at least 3 months to solve all questions. Okay, so I just heads up there. Also, book 1 is completely undone, right? It's part of your syllabus as well. So the exam date, it's same date as Excel AAS, that's like 18th December. So you have about like month plus over it, but treat it as your screening partner. Let's see if you're capable of doing your exam, right? But it says it's a true test for yourself. You follow that you're right track. Hardcore, you should think of alternate route out there. Both of these would help you. Much time. That's the point when you're gonna face it. Okay. So yeah. It's a good benchmark. Because you can cover the rest, no matter how behind you are. Okay. If you wanted to be part of. it's unofficial. I'm not really sure. Election জন্য পরেও হতে পারে, so take over করে, but last time I heard is 24th to 31st. Right, let's move on. So screen দেখো, so you have chapter 6 deformation. So এখানে হচ্ছে first thing is stress and strain, and then we have আরেকটা topic here আমি দেখাই রাখি 6.2 মনে হয় এখানে পরে আসে, I want to explain what's going on here. So 6.2 হচ্ছে এটা elastic deformation, plastic deformation, these stuff, right? Strange একটা জিনিস is that they do this the other way around. So it actually এখানে start হওয়ার কথা. So we are supposed to start and learn about springs, and then we learn about stress and strain. Okay, I don't know why they did this in the syllabus. Ultata course. So I'll start with this first. Okay, this is the one that you know from your O levels, right? So can you go to page number 14? Right. A pager পাশে উপরে heading তো একটা helical springs. You have this topic in plenty when it comes to your practicals. So there are a few topics here that are truly there actually just for the practicals. Those are deformation and electricity. So electricity is like a must question in your practical. Deformation, moments, এগুলা হচ্ছে practically খুব often আসে. And once in a while they'll throw you something very random. For example, thermophysics, which we don't have, but they'll give you an experiment. It is very doable, so don't worry about that. But আগে থেকে বলে রাখলাম যে আমাদের a practical syllabus is very reliant on this topic, deformation approach. You have electricity, so yeah, right. So you have your spring here, and a helical spring is essentially this. Okay, so why is it called a helical spring? Because it takes the shape of something called a helix. And helix হচ্ছে একটা staircase এর মতো দেখতে, spiral staircase থাকে না, basically that shape, and we make a spring out of it. So Hooke's law, the person who came up with it, Robert Hooke, right? He found that if you wind your wire in this particular manner, right, the material starts to behave differently. So now we'll learn why do we have this chapter in A levels, right? O levels so A levels say we'll learn two things here. One is the property of this, what you see here. This is not a material, it's a shape. Spring is a shape, okay? And then we'll end up with learning the property of the material that the spring is made up of. Their behavior very different. So all I will say, when you learn about springs, we never thought about what it is made up of. We just knew that it's a spring. It probably could be copper, it could be aluminum, it could be iron, right? But that never was the concern for us. We were always bothered about what does the shape do, right? And with shape ja kore, it's very limited. It's what we call the Hooke's law. Hooke's law J idea. But then, people started wondering, not everything on, in material science is a spring, right? You can have like a rod here. Or a rodder behavior ta এরকম তো spring constant এই সব দিয়ে কাজ হচ্ছে না. So how do I know this behavior? তখন we have some improved quantities out there like stress, strain, and Young modulus. So just to give you a heads up, spring is a shape. Shape behavior, we do the stuff we did in O levels. force, extension, spring constant, right? Literally naming in the spring constant. It's only valid for what? Springs, right? And then we learn how to deal with material, like wood versus steel. Which one is like better, stronger, weaker, whatever the properties are, right? So we're done with the second part of the chapter. So first we'll just do the spring version. So you have your spring here, helical spring, and a few things before I start my topic. So you have this length that's been labeled here. This is referred as the original length. So এটা হচ্ছে the unextended length of your spring, original length. And then what you do is you add some mass to it and apply a force to it, and you notice that this spring extends. Now, turns out the length that the spring extends to is not really of any importance to us. When it comes to springs, right, the thing that matters more is the what of the spring? Extension, how much it changes the length by, not what the original length is, okay? Not what the new extended length is. So the extension, the extra that's happening, that's what matters more, right? So when you take a spring and you add some force here at the bottom, right, you'll find that the spring will extend, right? And that new length that you see here, that new length is the extended length. And once again, that's not our concern. We are concerned about the extension. So this is the extended length. And then if you look at the extra additional length here, that is what matters for us, okay? So this is your X and this is your extension. This is the force applied here, niche F. Achha, so question for you. Let me try to show you what's happening here. So if I take a spring, right, and I attach some mass to it, it will extend because it shows certain behavior. So shall I do a couple of minutes? So I take my spring, I add this vernier caliper here, and this thing has extended, okay? Now, this spring, right, or this material, if I take the vernier caliper out, becomes exactly like it was originally, right? So we referred these materials as what? Elastic material. Elastic material maneki, they change their shape when a force is exerted, and they go back to their original shape when the deforming force is removed. So তোমাদের হচ্ছে জিজ্ঞেস করো what's an elastic material, right? And students say it's a material that goes back to its original shape. Oita is not the answer. The answer is when a material is stretched, it deforms. And when the deforming force is removed, what does it do? Go back to the original shape, okay? So that is your elastic material. However, certain materials, you apply the force, right? And it goes to a certain point and you release it. It doesn't go back to the original point. It goes back, but it doesn't go back to the original point. We refer them as what material? Plastic material or inelastic material. You get my point? Now, the reason why you are taught springs, which is very niche, like, where do you have springs? You have springs in your mattresses, maybe in your car suspension, or at maximum in the pen, right? So it's not like a very widely used thing to begin with. So why do we focus so much on this, right? Reason hoche, this is the only thing that we have in our syllabus, right, that does both. And does both very well. So it'll show a perfect what behavior, elastic behavior. And then you go beyond a certain point, it becomes what? Plastic, right? On top of that, it shows some other behavior that's very unique to it. So the first one is when you apply a force, it undergoes extension, but the extension is directly proportional to your force. Very few material out there does that. So এখানে যেটা হয়, আমি 1 Newton দিলে যদি 1 centimeter বাড়ে, 2 দিলে 2 হবে, 3 দিলে 3 হবে, 4 দিলে 4 হবে. So this is only done by a spring. And that's the reason why we use springs where mostly in practical scenarios. কোথায়? না যে যা ফোর্স দিচ্ছ এটার সাথে ইকুয়ালি বাড়তে থাকে. The idea that the more force you apply, the equal amount it extends, right, is applied in what device that we know of? Yeah, তোমার spring balances. Literally নামই তো spring balance, right? What's inside this? A spring. And as you pull this, a spring to extend hoy, and the extension is directly proportional to the force you exerted, and that's it, right? Why can't I use, let's say, a rubber band for this purpose? Rubber band, so if I have a rubber band here, why can't I use like a rubber band balance, right? Like spring balance মতো rubber band balance কি problem? 1 Newton একটু বাড়বে, 2 Newton অনেক বেড়ে যাবে, 3 Newton it'll tear or something happens, right? So the extension is not what for a rubber band? Linear মানে কি equal হচ্ছে না. So therefore it's not easy to calculate or estimate what's going to happen. Okay. Anyway, so you have your spring here and force apply করা হচ্ছে F. Now, what we're going to do is we'll plot a graph here. So each chapter took graph heavy, and the graph we'll plot is your force versus extension graph. And right away, you'll notice that something is odd about this graph. What is odd about this graph? It odd O level still chilo. Ki odd a graph? No. What? Yeah, force is dependent here, extension is independent, right? That's not true. Am I not applying force and because of that I'm getting an extension? Isn't it that the force is independent and the extension is the dependent quantity? And where does the independent variable always go? X-axis, independent, the one you change, right? Always goes where? X-axis, right? And the dependent always goes where? Y-axis. This is flipped around. Now, why is it flipped around? It's a matter of convenience. We'll see right now. তুমি উল্টাটা করো তোমার সবকিছু উল্টা আসে, like it doesn't really make sense having this graph. So at the end of the day আমার কি দরকার, like a nice looking graph or actual usable data? So usable data জন্য this is the better version. Okay, what if they ask you for force versus extension, like extension versus force? Nothing changes, it's just a reverse graph, মানে reflection along the y equals to x line. গ্রাফটা এদিকে গিয়ে যদি এদিকে যায় ওটা ওদিকে গিয়ে ওদিকে যাবে. Okay, but anyways আমি বুঝাচ্ছি জিনিসগুলো, let's not rush. So you can do the graph plot for force versus extension. We find that it's a straight line passing to the origin, and then it bends when it undergoes permanent deformation. Can you guys tell me, will it bend this way or will it bend that way? Up or down? Which way does it bend? Why? Yeah. Exponentially increase করে না. আচ্ছা. Okay, what do you think? Is it, I know it's a guess most likely, but what do you think? Is it easier for you to stretch a material that's withholding its integrity when it's still as it is, it's still elastic? Or do you think it becomes loose once it loses its structure? Right, so when is it easier to stretch? When it's within the elastic limit or beyond the elastic limit? Beyond. Okay, so it turns out so basically so what happens is when you apply a small force here, what brings it back here? Electrostatic forces from the bonds inside. That's what's happening, right? So I'm just stretch bonds are strong enough to go back again. Stronger than the force I apply. But once you take it and permanently deform it, right, what happens? Bonds are broken, and the bonds are broken or there are few bonds out there pulling you back. Wouldn't it be easier for you to stretch now, right? But are all the bonds broken? No, because the material is still there. It's just what now? Little loose. Why? It has undergone permanent bond breakage inside. It will become something like this. So like that, right? Do you see this part here? So what happened here? Is it has all the bonds broken there? No, but there has been a major bond breaking scenario here because it has what now? Permanently deformed. You get my point, right? So এটা গ্রাফ থেকে একটু দেখতে হবে তোমাদের. So গ্রাফে দেখো কি হচ্ছে, like what's the logic behind this? And I don't want you to memorize the graph, so I want you to show the logic so that যে কোনো অ্যাক্সেস দিলেই তোমরা লজিকটা দিয়ে বের করতে পারবে কি হচ্ছে. So এটা বের করার একটা খুব interesting and simple way আছে, and you'll use this for any subject you have, especially electricity that are back করে. The change-টা কিরকম হচ্ছে, okay? So look at this. This is the technique to use. What you do is you apply a certain amount of force here. Okay? This is the force I've applied. So the force I've applied here is this much, okay? And because of that, I get an extension that is this much. Do you understand what I mean? that for this amount of force, that's the amount of extension we can attain. Are you with me so far? Now, what I'll do is I'll apply the same amount of force up here. So if I apply the same amount of force up here, the amount of extension that I get for the same amount of force cannot. Do you see this part there is the same as the one at the bottom? Am I getting the same amount of extension or am I getting more extension? Way more extension, right? And that tells you your material has permanently deformed. And that's a way to check whether your graph is right or wrong. Because অনেক সময় এক্সামে কি করে force extension উল্টোপাল্টা করে দেয়, students are now confused. Should it go up or should it go down? Check for, does the material undergo more deformation for the same amount of force or not? If it does, tell you your y-axis is force and x-axis is extension. I'll add notes to this, but আশা করি তোমরা বুঝছো এটা। I mean, it are great fixing with error. This part is the one that's there. A red part shade is also what? The same amount of force, right? But as I apply the same amount of force, do you guys see that the amount of extension here is the extension isn't this much bigger compared to the previous one? So am I not getting more extension for the same amount of force? And this is what happens when your material undergoes permanent deformation. Now, a couple of you said that what if the graph went up like that? For a very large amount of force, I'll get a very small amount of what? Extension, which is not true. Permanent deformation hole সেটা হয় না. Permanent deformation হলে কি হয়? উল্টাটা হয়। যে for a very small amount of force, you get a very large amount of extension. কিন্তু উল্টাটা হয়ে যাচ্ছে। So yeah, that is the reason why the graph bends downwards. Okay. গ্রাফটা কখন উপরে যাবে? I mean, it's an obvious question, but তোমরাই answer করো। গ্রাফটা উপরে কখন যাবে? Yeah, exactly. Extension আর force যদি হচ্ছে reverse করে দেই, তাও করে দেই তোমাদের যেহেতু confusion. So extension and force reverse যদি করে দেই, the graph will go like that. Rubber bands have random graphs. Like, you know, it's not a straight line, not a curve. It's a mix. We have that happening for a while. Acha, so সবাই একটু স্ক্রিনে একটু তাড়াতাড়ি করি আজকের মধ্যে I want to wrap this initial part. So a grapher মধ্যে there's a point till which the graph is a perfect straight line. Is that point? Okay. A point পর্যন্ত the graph is a perfect straight line. What do we call this point? Limit of proportionality. Very good. So এটাকে বলা হয় limit of proportionality. Limit of proportionality definition হচ্ছে it is the point till which force and extension are what? Directly proportional. Okay. Limit of proportionality. And a point পর্যন্ত আমি materialটা আনি and I remove the force, the material goes back to its original length. What can I call this point? A point পর্যন্ত যদি আমার materialটাকে নিয়ে যায় and I remove the force, right? It goes back to the origin. What can I call this point? Elastic limit. Elastic limit. Okay. Oh, you guys don't remember this? So at the point at which your material shows elastic behavior, right? What do we call that point? Elastic limit, right? So this is your elastic limit. Now, this point also had another name. What was it? This exact point that you see here. So it has elastic limit একটা নাম, limit of proportionality একটা নাম, and then there was another one. Yield point. No, yield point. No. What is the other name of this point? Yeah, it's the Hooke's limit. You guys seem a little slow. কি হচ্ছে? মানে মনে নাই নাকি আমরা করি নাই? It was part of our syllabus, right? Yeah, so this is the Hooke's limit. Now let me explain. একটু বোর্ডে দেখো এদিকে স্ক্রিনে it's now going to change. এটা I mean, যদি মনে না রাখতে পারো, it's kind of good. কারণ এটা actually wrong. আচ্ছা, so wrong না, মানে not really appropriate. So the thing is, students eventually যারা মনে রাখতে পারে, তারা মনে করে যে the elastic limit, the limit of proportionality, the Hooke's limit, they're all synonyms. Synonyms মানে কি? They're just the same thing with different names, right? Turns out these three are entirely three different properties out there. But for a spring, right, your typical spring, all these 3 points happen to lie at the same place. You could say it's a coincidence, okay? So spring A, your elastic limit, Hooke's limit, limit of proportionality, all happen to be where? At the same place. The struggle with students in AS is that we will now see materials, these points are not at the same place, and that confuses them, okay? But that's what the reality is. So if you look at any material out there, like wood, plastic, steel, whatever, right? Or their elastic limit, limit of proportionality, Hooke's limit are at different places. It's just helical spring, they happen to be at the same place, right? I'm বুঝাচ্ছি ওটা, don't worry. That's the main part of our chapter. And in প্রথমের যে regionটা, this part here, right? The one that's shaded blue. What region is that? It's a region in which the material, if it's stretched, right, and the force is removed, always goes back. Elastic region, right? And once you cross this point, the Hooke's limit and the limit of proportionality and elastic limit, right? What does the material become? Yeah, so that's the plastic region. So this is the elastic region. And for it to the plastic region. Right, so I'm going to show you how is it possible that elastic limit, limit of proportionality, and Hooke's limit, they all can have different places. Does the area under the graph give us work done? We will learn that. Entirely work done, the area under the graph gives us elastic potential energy or elastic strain energy. We have a class just dedicated for energy because the topic energy is important. Right, so let's move on. Let me show you materials that have different location of elastic limit and limit of proportionality. Right, show it to screen. It will focus on previous about day. So we have this graph here. This is a material graph, and we have this is a very important graph in our syllabus. So let me explain some parts here. So this last part that you see here is the point till which your material is elastic. এটা তোমরা বলে দিতে হবে because elastic limit হচ্ছে graph দেখে বলা possible না. It is something that always has to be mentioned. And this material doesn't have any what point. A material at one point exists from the previous one. Yeah, there's no limit of proportionality. Is there any part on this graph where you think that the force and extension are directly proportional? Briefly, but can you say there's a region where it's like that? No, right? So this material obeys elastic law on a elastic behavior, but doesn't show what behavior? Proportional behavior. Okay, proportional na. It's a kisher graph. This is your rubber band. Okay, so rubber band graph ta mone rakha khub easy. It looks like a rubber band. Right, now I'm going to show you another graph right now. Eta dekho. How does it look beyond the elastic limit? It breaks. Elastic limit to break by rubber band. Rubber band is no plastic part. If you try to tear the rubber band up, and it breaks. There's no permanently deformed rubber band. Acha, a graph ta dekho ekটু. Blue graph ta. Blue graph ero last point ta hocche your elastic limit. Okay, so a point of the material will go and it will break, right? But do you think this material has a limit of proportionality? Yeah, it does, right? Some part that you can zoom in pretty quick. Isn't that first part a bit of a straight line out there? It is not substantially large at proportionality, but it is there, right? So at that point is your limit of proportionality. Now, why am I showing them? Okay. Correct. Let's very, very important fact that is the core of the topic here. Hooke's law states that a material will show linear relationship and simultaneously show one behavior, elastic behavior. So Hooke's law states that force and tension are directly proportional to the one limit, elastic limit. Some springs are famous for Hooke's law, because যত স্ট্রেচ করি তত ফোর্স বাড়ে, যত ফোর্স কমানো এক্সটেনশন বাড়ে আর যত ফোর্স কমায় তত এক্সটেনশন কমে সো ফোর্স and extension are what for a spring directly proportional. Also the material shows what behavior while it's directly proportional elastic behavior. So any material that does both it's linear and also elastic we call that material or consider that material of what law. So that's why if you look at this graph here, the one that we drew earlier, a point পর্যন্ত the material shows what behavior, elastic behavior. A point পর্যন্ত the material shows what kind of relationship, linear relationship. So wouldn't this point also be the Hooke's limit? Because এটা পরে, why is it not Hooke's limit? Because it's no more linear and no more elastic. You get my point? So that being said, can you tell me, does a rubber band obey Hooke's law? See if you can answer this. It's a very common question in your syllabus. Does a rubber band obey Hooke's law? The rubber band that I have labeled there. No. Why not? Which property has it failed? Yeah, the linear relationship. So it is elastic, definitely, but it is not what though? Proportional. Okay. Can you tell me this blue line that you see here, does that obey Hooke's law? Till which point? Very good. Okay. Cano ei choto parttate isn't it elastic? And isn't it also proportional? So now I can say that this rubber band does obey Hooke's law till that place, right? So what would that place be then known as? Hooke's limit, right? And if you understand basic logic here, Hooke's limit is always going to be which point of your material? No. What is different? I think I asked the question too soon. You guys are going all over the place. এই যে এদিকে দেখো আমি আরেকটা গ্রাফ ড্র করি আশা করি this will solve the confusion. So this graph is a straight line. এটাতে কোনো elastic limit নাই. What does this graph belong to? This is the graph for Play-Doh. Play-Doh থাকে না the mold করা যায় যে. So এই Play-Doh তে যেটা হয় certain qualities of Play-Doh ওইখানে তুমি যদি 1 Newton press করো it goes down 1 centimeter, 2 Newton দিলে 2 centimeter, 3 Newton দিলে 3 centimeter. Basically the force you apply is directly proportional to the deformation it gets. But there's a catch though. As you compress it to a particular point or stretch it to a particular point and release the force, what does it do? Stay there. Change hoina, right? So does it show elastic behavior? No, right? No, it doesn't show. Does it show linear relationship? Yes, right? So my question for you, does this material obey Hooke's law? No. And which one did it fail? No. Elastic limit, okay? So the idea is that your material needs to be both elastic and proportional to be obeying what law? Hooke's law, right? So coming back to my question, what is the criteria that your Hooke's limit needs to obey? So you'll always find that the first point of either limit of proportionality or elastic limit, right? The first point is always the Hooke's limit because wouldn't the first point be the one that covers both of them? Right? So always it's a tip for you, like shortcut model. So in the graph Hooke's limit is always going to be the earliest point of whether it's linear or elastic. Because that's the point to which what would be obeyed, both the properties, right? So yeah, that's the graph that you have here. Our definitions go daily. Is there anything else that I need to show you guys? No. Okay. So that's the first part of our topic done. The graph analysis of springs. What type of questions are asked from this part? Generally, does it obey Hooke's law or not? Or কোন গ্রাফটা কি represent করে? Which is the elastic limit? Sorry, elastic limit now. What is the limit of proportionality? Those kind of things. Okay, definitions below. This chapter used to have 21 definitions. Now they've brought it down to 11, which is a good thing because definitions মানে তো they're fixed and একই জিনিস বারবার জিজ্ঞেস করবে। 21 ছিল tough, strong, brittle, hard, তারপর হচ্ছে you had ductile, malleable, all those things. Yeah, but তোমরা যদি chemistry শিখো, it's actually a little primitive. যে ductile কে নিয়ে drawn into thin wires, malleable হচ্ছে beat into thin sheets. Hey, that's not actually the definition. There's a much more scientific definition, which এখন ওরকম নাই আর।
What is the actual definition
of ductility? It's the ability of a material to undergo large amounts of tensile deformation. Our malleability is the ability of a material to undergo large amounts of compressive deformation. So drawn into thin wires is tensile, or pressed into thin sheets of compressive. That's the right term. Yeah. So rubber band হচ্ছে elastic, but not linear. Our clay হচ্ছে linear, but not elastic. For Hooke's law, what should the ticks be? No, when it's actually screen it, your rubber band is elastic but not linear. Our clay হচ্ছে linear but not elastic. So none of these obey what law? Hooke's law. So if they did obey Hooke's law, what would be my criteria here? Yeah, linear and elastic. So one of you asked what's the requirement. That's the requirement. They need to be both linear and elastic simultaneously. Okay, let's see some of your question. What about materials in plastic limit? How do you know what the elastic limit is if there's no linear part of the graph? You can't really find elastic limit from a graph. It has to be mentioned to you experimentally. Limit of proportionality and Hooke's limit difference key. Limit of proportionality হচ্ছে যে পয়েন্ট পর্যন্ত force and extension equally বাড়ে, আর Hooke's limit হচ্ছে যে পয়েন্ট পর্যন্ত force and extension equally বাড়ে and also the material is elastic. So elastic now is not obeying Hooke's law or Hooke's limit. Can you explain the limit of proportionality? Limit of proportionality যেটা যে পয়েন্ট পর্যন্ত the graph is a straight line. Hooke's limit and limit of proportionality is same all the time. No, not same all the time. দেখাই কোথায়। Sorry. Yeah, it doesn't. So an elastic material doesn't need to be a linear graph, like rubber band. Rubber band is very elastic. So what is the graph? Non-linear. আচ্ছা সবাই একটু স্ক্রিনে দেখো। I want to clarify something because এই কোয়েশ্চনটা অনেকের কাছে আসছে। এই নিচে যে অরেঞ্জ কালারের গ্রাফটা ড্র করলাম, right? Do you think that material obeys Hooke's law? There's a definite answer here, yes or no? Yes. Why? Because is it a straight line? Yes, so it's linear, and it also has a what point? Elastic limit. So wouldn't that mean that this region behind this is elastic and also what? Linear. So therefore, what does it obey? Hooke's law. Okay. So this is your Hooke's limit as well. এরকম material পাওয়া খুব difficult, but হইতেই পারে যে it's continuously going to be linear, but meanwhile, what did it lose in between? Is elastic behavior. Okay, it exists, by the way. Certain kind of steel does that. Why is the elastic limit the same for springs? The right thing. Blue line doesn't obey Hooke's law, but has a Hooke's limit. No, what? No, blue line does obey Hooke's law. আচ্ছা অনলাইনে তোমাদের অনেক কনফিউশন হচ্ছে কেউ আমাকে বলতে পারবো why does the blue line here এই যে উপরের blue লাইনটা obey Hooke's law? Very good. So it's both elastic here because elastic limit to eta তার মানে কি elastic তো পুরো জায়গাটাই, right? Also it is a what line at that small part? A straight line. So wouldn't that like confirm with both of the properties out there? So it's obey Hooke's law. Why is the elastic limit, limit of proportionality, and Hooke's limit the same for a spring? Why is it same? এই যে spring এর জন্য elastic limit, limit of proportionality, and Hooke's limit সব same. কেন? বললাম তো, it's a coincidence. It's a coincidence that the point till which the material is linear also happens to be the point till which the material is what? Elastic. So till what point would it be obeying Hooke's law? Till that same point as well. Okay, it's just a coincidence. Okay, it's not like unique something. It's just ওই spring এর জন্য elasticity lose করলে linearity lose করে. So wouldn't that be the final point which it obeys Hooke's law? Can we find the elastic limit of a spring without experiment? No, there's no way of doing that. You have to stretch the material and test the material. Okay, next class here we will continue with the energy interaction of springs.
Exam you took, right? I didn't get my paper.
We can have the
Yeah.
Did you look up front? On the papers are up front.